Section. Introduction. We're here to discuss the fascinating capabilities of large language models, LLMs, and how they can be fine-tuned to perform a variety of tasks. Fine-tuning these models to align with human instructions is a key step in unlocking their full potential. While some studies suggest that these models can follow human instructions well with a small amount of fine-tuning data, it's often necessary to increase the amount of data when we want to expand the range of tasks or improve performance on a specific task. However, increasing the amount of fine-tuning data on a large scale can present new challenges. For instance, we've noticed a significant drop in performance on the closed-book question answering (CBQA) dataset when we substantially increase the amount of fine-tuning data. We believe this drop in performance might be due to the loss of previously learned and stored world knowledge in the pre-trained models. To test this theory, we first confirmed that the CBQA dataset relies on the world knowledge stored in the models for making inferences. Then, we showed that the significant decrease in performance on the CBQA dataset is due to large-scale fine-tuning altering the model's parameters, which can lead to the loss of world knowledge. This suggests that there's a conflict in vanilla supervised fine-tuning between improving performance on downstream tasks and maintaining world knowledge of LLMs. Our findings indicate that vanilla supervised fine-tuning with a large amount of data can lead to the forgetting of parametric knowledge stored in LLMs. Ideally, we would like to designate a specific region within the model to store world knowledge, similar to how certain areas of the human brain are specialized for memory. This would allow us to freeze and protect the parameters in this part during the fine-tuning process, preventing world knowledge from being disrupted. However, due to the complex nature of large language models, identifying these regions is quite challenging. Instead of trying to identify these regions, another solution is to keep all the parameters of the model by using plugin-based fine-tuning. This method fine-tunes the model by freezing all the parameters of the backbone model and binding parameter changes to an additional network. While this approach technically allows for the recovery of world knowledge stored in the backbone model, it doesn't fully solve the issue of knowledge forgetting. To address this, we propose using a mixture of experts (LORMOE) architecture, which introduces multiple experts where data with different characteristics are routed to the corresponding experts for customized processing. We hope to introduce multiple plugins as experts, allowing some of them to access the backup, while others can perform downstream tasks. In this paper, we introduce LoRAMoE, a plugin version of LoRAMoE designed to alleviate world knowledge forgetting and simultaneously enhance the LLM's capabilities of solving downstream tasks. LoRAMoE changes the model's architecture by adding multiple parallel plugins as experts in each feed-forward layer and connecting them with routers. We also propose using a localized balancing constraint to split the experts in each LoRAMoE layer into distinct groups. One group is dedicated to downstream tasks, while the other focuses on aligning world knowledge within the backbone model with human instructions to alleviate knowledge forgetting. Our experiments show that LoRAMoE can effectively prevent the world knowledge in language models from being disrupted by large-scale fine-tuning. We also found that LoRAMoE can effectively route different types of data to respective experts during the fine-tuning phase without interfering with the original parameters of LLMs. Furthermore, we found that learning on various downstream tasks also benefits from our method, suggesting its potential in multitask learning. In summary, our contributions are as follows. 1. We discovered that significantly increasing the amount of supervised fine-tuning data can severely impair the world knowledge inside the LLMs, due to its great modification to their parameters. 2. We introduced a new trainable plugin for LLMs, LoRAMoE, which can automatically route different types of data to respective experts during the fine-tuning phase without interfering with the original parameters of LLMs. 3. We demonstrated the effectiveness of LoRAMoE through extensive experiments. We were able to maintain stable knowledge in the model when scaling up fine-tuning data, and we also saw considerable improvement in performance in other tasks. Section Summary. Large language models, LLMs, have shown impressive capabilities, but increasing the amount of fine-tuning data can lead to a decline in performance on certain tasks, indicating a conflict between improving performance and maintaining world knowledge. To address this, we propose LoRAMoE, a plugin version of Mixture of Experts, which introduces multiple plugins as experts to preserve world knowledge while enhancing downstream task-solving abilities. LoRAMoE effectively prevents knowledge forgetting by balancing the importance of experts and fostering collaboration among them, resulting in improved performance on various tasks. Section: Conflict between expanding fine-tuning data and retention of world knowledge in LLMs. In this section, we explore the tension between expanding fine-tuning data and maintaining world knowledge in large language models, LLMs. We carry out several fine-tuning tasks on the LLM using a wide range of datasets. Our findings suggest that the LLM's world knowledge is significantly compromised when we expand the fine-tuning data. To understand the impact of large-scale fine-tuning on the LLM's world knowledge, we create a large dataset that includes a variety of tasks. These tasks include closed-book question answering, CBQA, CO reference resolution, natural language inference, NLI, abstract summarization, multilingual translation, reading comprehension, and text classification. We expand the training datasets to 5 million using data augmentation methods. More information about our fine-tuning data composition can be found in the appendix. We use Llama 2 to 7B as the base model, as it is one of the most prominent and widely used open-source LLMs in academia today. For evaluating the world knowledge, we use CBQA as a key benchmark, referring to previous work. We carefully select parts of the CBQA dataset without train-test overlap for our testing set, namely filtered NQ and filtered trivia QA, to better analyze the world knowledge of models. For evaluating performance on other tasks, we use the Open Compass framework to run the evaluation process. During the expansion of fine-tuning data, we noticed a diverging trend in performance across different types of tasks. On some tasks, such as summarization, NLI, machine translation, etc., the performance of the fine-tuned model initially increased significantly and stabilized at a promising level. However, there was a dramatic drop in the model's performance on the benchmark measuring knowledge capability, e.g., Trivia QA, NQ, Hotpot QA, even falling below the baseline. As the training data expanded, a continuous decline was observed. Moreover, in the filtered test set, the collapse occurred earlier than in the original one. We then investigated the reasons behind the decline in performance in world knowledge benchmarks with the expansion of fine-tuning data. We found that the performance on world knowledge benchmarks heavily depends on the knowledge and skills learned during the pre-training phase. To explore this relationship, we fine-tuned solely on the CBQA dataset with 250K samples and ran evaluations on the test sets without train-test overlap. The results showed that the performance on these benchmarks can be significantly improved through naive training. However, most of the improvement comes from the first 1% of the training process, approximately 1,000 samples, and further increases in the training sample do not significantly improve the performance. This phenomenon makes sense. In the early stages of fine-tuning, the model quickly learns to follow human instructions through training data and align the world knowledge already stored in the model with the instructions, thereby increasing the performance of CBQA. However, due to the limited overlap between the training and testing data, the knowledge in the test set is difficult to incorporate during training, so more samples do not improve performance. Therefore, the model's ability to complete the world knowledge benchmark heavily relies on the knowledge and skills acquired during the pre-training phase. We hypothesized that the significant drop in the model's performance on CBQA comes from the disruption of knowledge stored in the LLM due to large-scale instruction tuning. To test this hypothesis, we used two distinct datasets for sequential fine-tuning of the model. First, the model was fine-tuned using instruction data excluding the CBQA segment. Then, we further fine-tuned the model with the CBQA dataset that had been separated before. The results showed a significant degradation in the knowledge capabilities of the fine-tuned model, and its performance was inferior compared to the original LLM. This suggests that the world knowledge within the model was compromised during the first stage of fine-tuning, resulting in the model's inability to forge the alignment between human instructions and the already disrupted knowledge in the subsequent stage of fine-tuning. Furthermore, we found that there is a significant change in the LLM's parameter during the expansion of fine-tuning data. Previous research has shown that models store knowledge within their parameters during the pre-training process. This further indicates the destruction of the knowledge stored in the parameters during large-scale fine-tuning, which results in knowledge forgetting. In conclusion, improving the instruction following capability and enhancing the performance on various downstream tasks of LLM through large-scale vanilla fine-tuning inherently conflicts at the parameter level with retaining the world knowledge stored in the model. Section Summary. In this section, the authors conduct experiments on a language model, LLM, using various tasks and datasets. They find that when the LLM is fine-tuned with large-scale data, its world knowledge is severely compromised. The expansion of fine-tuning data leads to a decline in the model's performance on knowledge benchmarks, indicating a conflict between improving task performance and retaining world knowledge in LLMs. Section. Methodology. We aim to improve the performance of language models across various tasks while maintaining their world knowledge. However, these two goals often conflict at the parameter level with traditional methods. To address this, we introduce LoRAMoE, a language model adapter that uses a mixture of experts, MoE, approach. This approach partitions different capabilities within distinct sections of low-rank adaptation, LoRA. First, let's briefly discuss the traditional MoE and LoRA methods. Then, we'll explain how LoRAMoE combines these two methods to leverage their strengths and resolve the conflict issue. The mixture of experts method allows for a significant increase in model parameters without a corresponding increase in computational effort. For large language models based on transformers, MoE replaces the standard feed-forward neural network layer in each transformer block with an MoE layer. This layer consists of n identical and independent feed-forward neural networks, known as experts, along with a gating function that acts as a router. The router models the probability distribution that determines the weights of outputs from these expert networks. In the MoE layer, the output is calculated based on the output of the attention layer in any given block. Each expert in the MoE layer has an output and a corresponding weight. The router can be represented by a trainable weight matrix. The MoE-based language model allows its experts to acquire varied competencies and focus on distinct capabilities through the routing mechanism. In our work, we use this MoE approach and fine-tune the experts to strategically distribute competencies, aiming to address the issue of knowledge forgetting. We freeze the parameters of the backbones and replace the feed-forward neural network layer of experts with LoRA to enhance the training process's efficiency. Low-rank adaptation, LoRA, has proven to be an effective and efficient way to adapt pre-trained models to specific tasks. LoRA updates a pre-trained matrix with a low-rank decomposition. The forward process with LoRA involves freezing the matrix and adjusting the magnitude of the changes on the original matrix made by LoRA modules. However, the forward process of LoRA differs from that of LoRAMoE. In LoRAMoE, LoRA is used as the expert network within the MoE architecture, primarily to facilitate accelerated training and optimization. Our goal is to resolve the conflict between expanding instruction data and maintaining world knowledge in the language model during the fine-tuning phase. In the MoE-based architecture, the router function focuses on different experts according to the instruction data categories, allowing them to divide their labor to complete the forward process. Inspired by this, we aim to extend the pre-trained language model architecture into a MoE-like architecture to tackle this conflict, while retaining its original strong language model capabilities. We freeze the parameters of the backbone model, allowing experts within LoRAMoE to leverage the existing world knowledge in the base model. For the feed-forward neural network layer in each transformers block, we define several parallel trainable experts connected by the router. At the same time, we replace the fully connected layer of the expert with a low-rank form to improve training and inference efficiency. During the fine-tuning phase, we adopt a strategy distinct from optimizing a single matrix with the entire instruction dataset. We substitute the linear layer with the MoE architecture, allowing the experts within the MoE layer to collaborate and learn the updated matrix. The experts and routing function work together during the training phase, enabling the experts to develop varied capabilities and efficiently handle diverse types of tasks. At the same time, low-rank adaptation has proven to be both effective and efficient in the fine-tuning of pre-trained language models. To enhance the efficiency and resource conservation of the fine-tuning process, we adapt the parameter matrix of the experts in the MoE layer into a low-rank format. This significantly reduces the parameters of the experts network, enhancing efficiency and saving costs during the fine-tuning process. Overall, the forward process of the modified linear layer, i.e., LoRAMoE layer, in the feed-forward neural network layer can be represented as a combination of the attention weight of each expert in the LoRAMoE layer and a constant hyperparameter, which is approximately equivalent to the learning rate. Section Summary. We propose LoRAMoE, an LLM adapter that combines the mixture of experts, MoE, approach with low-rank adaptation, LoRA, to enhance the language model's capabilities while retaining its world knowledge. LoRAMoE strategically distributes competencies among experts within the MoE architecture, leveraging the strengths of both methods and effectively addressing the conflict between expanding instruction data and maintaining world knowledge. Section. Mixed distribution dilemmas for expert balancing. When we're fine-tuning a mixture of experts, MoE, model without any constraints, we often find that a small number of experts end up getting a lot of attention from the router mechanism. This can be seen in Figure X. This imbalance can be hard to correct because the experts that get more attention early on in the training process get optimized faster, and therefore, get even more attention from the router. This phenomenon has been observed in previous studies as well. A common way to balance the use of experts is to use the variation in the importance of the experts as a loss function. This is done with the aim of making each expert equally important. This approach assumes that the training samples used to optimize the MoE model come from a single distribution, which means we don't need to consider the different sources of the data. However, this assumption often doesn't hold true when we're fine-tuning data that includes both factual knowledge QA and other tasks. This can lead to significant biases, especially when dealing with datasets with different distributional characteristics. Traditional balancing constraints, which aim to distribute the training samples evenly across all experts, can lead to inaccurate parameter estimation. This is because these constraints don't take into account the inherent differences in data representation and importance across different categories. Our approach, which we call LoRAMoE, strategically assigns data to experts based on the observed imbalances, not uniformly. This allocation is controlled by a set of weights that reflect the varying importance and representation of different data categories within the overall dataset. This method is crucial in addressing the challenges posed by uneven data distributions. By tailoring the distribution of training samples to each expert based on the inherent disparities in the data, LoRAMoE facilitates a more accurate and representative parameter estimation. This nuanced approach to data distribution allows for a more effective fitting of the model to diverse data subsets, significantly enhancing the model's predictive accuracy and generalization capability. To illustrate this concept, let's consider a simplified model where our training data is sampled from a mix of two Gaussian distributions. The means and variances of these distributions are implicit. The proportion of training data from each distribution is denoted as P1 and P2, where the sum of P1 and P2 equals 1. We assume that P1 is less than or equal to P2. When a MoE model fits the proposed distribution with balanced weights M, the likelihood of the model given the data can be expressed as follows. The optimal mean value for the first distribution satisfies certain conditions, which are 0 when the fitted distribution is in the same family of mixed distributions as the sampling distribution. In this equation, we can replace part of the summation with the empirical estimate of the mean of the input X. For an ideal routing network, there must exist a distribution such that the data allocated to this distribution is independently and identically distributed with one of the peaks in the sampling distribution. Let's assume this distribution to be the second one. In this case, if M is greater than or equal to P1, then the fitting result for the first distribution will be a certain value. Based on the chain rule of differential derivation, we end up with a certain result. The inverse result can be derived similarly. Therefore, the best training error is achieved only when the mixing coefficient M of the prior distribution is consistent with the actual sampling distribution weight P1. In the next section, we will introduce a localized balancing constraint algorithm, which uses adaptive balancing coefficients to explore the optimal data distribution mixing coefficient. Considering the aforementioned dilemmas, we introduce a strategic approach as depicted in Figure X. Unlike previous efforts that solely focused on distributing the learning data among all experts evenly, LoRAMoE can methodically segregate the experts into two distinct groups, one of which concentrates on learning massive tasks, while another focuses on aligning the world knowledge with instructions. While all experts within the same group are balanced, this balance is not uniformly applied across groups. We define the importance matrix of LoRAMoE layer, and each element in this matrix denotes the sum of router values of a certain expert for a certain training sample in a batch. We then define the coefficient matrix with the same size of the importance matrix, corresponding to the importance matrix. Each element in this matrix denotes the importance coefficient of a certain element in the importance matrix. We categorize the instruction data into two distinct groups, CBQA and other downstream task data. The CBQA serves to enable expert groups to align human instructions with knowledge, whereas the remaining data is allocated to task-focused experts to boost task performance. We define the localized balancing constraint loss to quantify the dispersion of the weighted importance matrix, which can be mathematically represented as a certain formula. Ultimately, optimizing the reduction of this loss achieves a balance in the importance of experts within the same group, while also ensuring different groups concentrate on different capabilities. The overall loss of LoRAMoE can be represented as a certain formula, where one part is the next token prediction loss of large language models and the other part is the localized balancing constraint loss for all LoRAMoE layers. During the fine-tuning phase, we freeze the base model and the trainable parameters are those of the experts and routers within the LoRAMoE layers. LoRAMoE significantly conserves resources compared to fine-tuning the full range of parameters of models. In the inference process, the router autonomously determines and assigns output weights to all experts, thereby obviating the need for pre-specified data types. Section summary. When fine-tuning a mixture of experts, LORMOE, model without constraints, a small number of experts often receive a disproportionate share of preferences from the router, leading to an imbalance. Traditional solutions for balancing expert utilization assume a single distribution of training samples, which can introduce biases and inaccuracies. LoRAMoE addresses this challenge by strategically assigning data to experts based on observed imbalances, resulting in more accurate parameter estimation and improved model performance. This approach allows for a more effective fitting of the model to diverse data subsets, enhancing predictive accuracy and generalization capability. Section. Experiment setup. In this section, we'll discuss how we set up our experiment for LoRAMoE, a language model we've developed. We've made a small change to the feed-forward neural network of the base language model, replacing the linear layer with a LoRAMoE layer. We've started with 6 experts in each LoRAMoE layer, half of them focusing on specific tasks, and the other half aligning the base model's knowledge with human instructions. We've set the control constraint strength and degree of imbalance to 0.1. For the experts that use a low-rank adapter, we've set 2 parameters, alpha and R, to 32 and 4 respectively. We've also set the dropout to 0.05 and the learning rate for both the experts and router in the LoRAMoE layer to 0.0002. We've used the same 3 million dataset for training as mentioned in a previous section. We've kept the base model's parameters constant, only allowing the experts and router in LoRAMoE to learn. We've used a batch size of 64 for our experiments, which were conducted on a 32-card A180G. Now, let's talk about the results. We've compared the performance of LoRAMoE with 3 million training samples to the results of directly applying SFT to the model or using LoRa tuning. The language model with LoRAMoE performed well on both world knowledge benchmarks and other tasks, showing that it can improve various tasks without forgetting knowledge. For world knowledge benchmarks, the model with LoRAMoE even outperformed the one fine-tuned solely with the CBQA dataset, such as on Trivia QA and Hotpot QA. Compared to vanilla SFT using the same amount of data, LoRAMoE improved world knowledge benchmarks by up to 64%, with an average increase of 35%. We also found that implementing the local balance expert loss improved performance on the world knowledge benchmarks. While LoRa tuning modifies fewer parameters than vanilla SFT, it still results in some forgetting of world knowledge. Its performance in CBQA is generally lower than the baseline, and there is an average decrease of 22% compared to direct single-task tuning. However, having multiple parallel experts helps balance world knowledge retention and the scaling up of fine-tuning data. For other downstream tasks, LoRAMoE performs close to or even better than direct SFT. For example, in all reading comprehension tasks, LoRAMoE performed better. We also visualized the use of the experts to confirm the effectiveness of LoRAMoE. We found that the routers can automatically assign specific tasks to experts with corresponding abilities during the inference phase. For example, the expert group that focuses on aligning parametric knowledge with human instructions is greatly used in world knowledge benchmarks, showing their important role in preventing world knowledge forgetting. On the other hand, experts assigned to focus on enhancing performance in downstream tasks are given more importance when encountering these tasks. In terms of related work, with the significant increase in the number of parameters in language models, parameter-efficient fine-tuning, PEFT, has become an important research trend. Several methods achieve more efficient fine-tuning of the language model, including prompt LoRa and prompt learning. PEFT based on LoRaRank is widely used, which introduces two trainable low-rank matrices for each fully connected layer, to achieve significant savings in training resources without adding additional inference computation cost. Mixture of experts, MoE, modifies the feed-forward neural network layer to sparsely activated experts, which significantly enlarges the model without remarkably increasing the computational cost. The exploration of MoE has attracted more and more attention in recent years. However, the vast majority of the works are trying to significantly increase the model parameters and reduce the computational cost. Some researchers have also proposed the utilization of multiple LoRAs to improve the performance of the models or to be more advantageous in some aspects. However, these methods take the data type as the input of the router during training, which necessitates prior knowledge of the data type during inference. We explored for the first time that the expansion of instruction data seriously damages the knowledge of the pre-trained language models during the fine-tuning phase. We further propose to address conflicts through the MoE structure and to utilize the LoRa to reduce resource consumption. Simultaneously, LoRAMoE is also an end-to-end approach that does not require a priori knowledge of data types for inference.